All right, it looks like we've got a good number of people on the line, so we'll go ahead and get started. Thanks so much for joining us for this month's US MAP webinar. My name is Harrison Dreves. I'm on the communications team at the National Renewable Energy Lab. I'm going to be running the technical side of the webinar, and I have just a few quick housekeeping items to walk through before we hand it over to our main act and get started here. Everyone is going to be muted by default in this webinar. We find it works best generally to kind of keep everybody muted so we can keep moving. If you're having any audio issues, the most common issue we see with WebEx is with computer audio. For some people, it just doesn't work well. If that's the case, we recommend switching over to phone audio. You can do that by choosing the audio option at the bottom of your screen and choosing switch audio, or just reconnecting and choosing the phone option when you first connect. If that doesn't work or you're having other issues, please use the chat function and select host, that's me, and just explain the issue you're having, and I'll do my best to help you out get that fixed. We are recording this webinar, and we are going to be posting that recording in a few weeks to the US MAP website under our webinars page. So if you want to go back and review any of this, just keep an eye out there in mid-September or so. It takes us a little while to get the video processed, but we are going to be putting a recording up on the US MAP website. We're also going to be conducting a Q&A at the end of the webinar. You can submit a question at any point during the webinar using the Q&A function in WebEx. Note, not the chat function. Please use the Q&A function if you can to submit your questions. So you can just type a question in there at any point. Make sure you've selected all panelists. That should be the default. And then we'll take a look through those at the end of the webinar and try to get to as many as we can before we run out of time. So with that, I'm going to hand it over to Joe Barry to introduce today's speaker. Joe?
Thanks, Harrison. Well, everybody, it's a real pleasure to get to introduce Colin Bailey today. I've known Colin for some time now and got to know him first when he was a student actually at Stanford, working to get his PhD in material science and addressing some of the key challenges with perovskite technologies at that point. Before, kind of going dark and behind the curtain, got involved as a young man with Cyclotron Road. He was also designated by Forbes as one of the 30 under 30s, but he's older now. So it's been a real pleasure to see him progress both, personally and professionally. And he founded Tandem PV along with his co-founder Chris Eberspacher. They're doing some really fabulous work. Have identified a number of kind of opportunities in the perovskite PV space with their company Tandem PV. And so I'm just super excited to hear what he has to say today. So with that, I'll turn it over to Colin and let him take it away.
Thanks, Joe. I really appreciate that intro. Pleasure to speak with everybody today, and thanks to US MAP for the opportunity to do so. It's still a little early in the morning here in California, so I'm gonna play myself some pump up music for a couple of seconds, so bear with me for a moment.
Think three sounds when you feel it kicking in.
All right, hopefully that worked. That's if MRS ever allows speaker walk up to the stage songs, that'll be my claim to play that song while we walk up to the stage. All right, today what I'd like to talk to you about is two topics. One short topic to give you an intro to Tandem PV and who we are, and then a main section speaking about end of life and how solar panels are disposed of and how that might have implications for this new field of perovskite solar panels. So first, a quick tandem PV overview. Tandem PV was born, as Joe mentioned, out of my graduate work at Stanford, where I had the fortunate position of being in the right time in the right place to do many of the seminal works on perovskite silicon tandems, whether through mechanically stacked or monolithic integration. And at that time, we really saw what the benefits and drawbacks were, both of tandems in general, as well as how to implement them. And when I graduated, really focused on what the market potential was. And here, anybody who tells you that solar panels are good enough and that more power in a solar panel really doesn't provide any additional value, they're lying through their teeth, since solar panels are there to make power. And for monocrystalline silicon, if you look forward, the line of sight is that they'll reach 25% efficiency, a pretty benchmark number, in about 2050. And that's a long time from now. With tandems, where you use two materials to combine and better absorb and convert the solar electricity, the solar light from the sun, you can reach 25% efficiency immediately and work your way to 30%. And that has really big effects on the market. Here in the United States, you can consider dropping by 33% or so across all sectors of installation, whether residential on your rooftop, commercial size installations on a Walmart, or industrial installations in a solar farm. And a 33% drop would be humongous. It would open up new markets across states where there is no solar whatsoever in the United States. But it's not simply enough to make a higher efficiency solar panel. We're here, I think all of us are here because we see this, the effects of climate change really bearing down upon us. And so getting to something that can scale is extremely important. And the way that we chose to do that was by making what's called a mechanically stacked tandem, where the perovskite goes onto a separate cover glass that can be switched out in a manufacturing drop-in style onto any silicon manufacturing line. And so we can use all existing silicon cell technologies. You can use all existing module fabs and simply replace the cover glass that's currently used with a perovskite coated cover glass and be able to upgrade the full 140 gigawatts of manufacturing capacity that exists in the world with silicon into a tandem without any major rework of how those solar panels are made today. And so it represents a lower switching cost. It represents a immediate added value. And it also has the benefit of lowering the overall manufacturing cost in dollars per watt of a solar panel. In the United States, we've been particularly focused on the US rooftop market, since that represents a sensible beachhead where the balance of systems costs are high and we can help offset those with higher efficiency. And indeed, when we speak to national and regional installers, to equipment distributors, they all are effluent about the potential for higher efficiency in their business, that it would change their game, that it would make their sales much more easy, that they could expand into new markets where they haven't been able to expand before, and that a tandem panel could in fact command an extremely high sales price because of this added value, up over $1 per watt, up to $1.25, which is where the highest efficiency, maybe 20–21% solar panels are priced at today. Tandem PV, as Joe mentioned, has grown from its founding in 2016 from a two-person company. We were incubated at Lawrence Berkeley National Laboratory at Cyclotron Road. And I want to give a shout out to them because I wouldn't be here without their help and support. And through that, we were able to gain some traction with government grants and seed round from silicon PV manufacturer back in 2019, and have continued on to today, where we're raising, and then hopefully in the next couple months closing our Series A financing round, and that's coupled with a large investment from a $2 million manufacturing grant from the DOE as we expand into the next phase of our business. And so want to make a little plug here that we are hiring quite a few people right now as we make this transition. So if you're interested in working with us, if you want to have a career in perovskites or in the next generation of solar panels, please visit our website at www.tandempv.com. And with the end of that shameless plug, I want to spend some time now talking about how we should think as a community about perovskites in this new technology and how they might be discarded of and recycled at the end of their useful life. And this is important for the manufacturers of perovskites. It's important for the policymakers that set local, state, and national policy around recycling and waste. But it's also important for the people who might buy these perovskite solar panels. And so this next section is all about level setting so we can have this conversation as we go into the future. And the first part of that level setting is who's actually responsible for the end of life of a solar panel. And the answer is different depending on where you are. In the US, if you buy the solar panel, you're responsible for getting rid of it. And that's actually going to be quite a headache for people who bought solar panels and put them on their rooftop in 25 years, because those solar panels are often hazardous and require special handling in order to get rid of them. In contrast to that, in the European Union, the manufacturer of the solar panel has that responsibility. They have the responsibility both to collect it from the end users at the end of life, and they have the responsibility to discard of them, whether waste or through recycling. And the second level setting here is to talk about what's in a solar panel. And for the purposes of this, since all regulations by and large have been made for the dominant form of a solar panel, which is right in front of you here, we'll be basing our discussion mostly on this form factor. And in this form factor, the main material is actually glass, this cover glass. And within that stack is a laminate of plastic, of silicon solar cells, and then again a plastic backsheet. On the back of that plastic backsheet is a junction box with copper wiring to connect each solar panel to the next solar panel. And then in general, that glass laminate is then surrounded on all sides by an aluminum frame to make it more durable. Now, what are the hazardous parts of that silicon solar panel? And even though somewhere between 80 and 90% of the weight of that solar panel is glass, the glass is not the hazardous part. In a solar panel, basically across technology options, the hazard is heavy metals. And these heavy metals can come in three different parts of the solar panel. They can come from the ribbons and the bus bar connections. In particular, if the solar panel is using tin lead solder, which is historically and even today still very, very common, then there's a significant amount of lead in the solder. The heavy metals can come from the absorber itself. If we're using perovskite, then that absorber may contain lead in itself. If you're using a thin film such as cadmium telluride, then of course it contains cadmium and tellurium. And the heavy metals can come from the electrode, where the example here, if we're using silicon solar cells, they often have silver fingers, and those silver fingers are deposited in a paste and fired, and that silver paste generally includes glass frit, and glass frit generally also includes lead. So the electrode can have silver and it can have lead, heavy metals within that part of the solar panel as well. And so now that we've determined we might have some heavy metals, then the next part in this conversation is about what is the regulatory framework that we have to think about as we decide how to discard those solar panels. And in the US, there's a somewhat complicated flow chart. You can go look this up on the EPA website. And the flow chart goes like this. Is it actually a waste? And it's actually a waste if you're going to throw it away. It's not a waste yet if you take it off your roof, but you intend to do something else with it in a second life type fashion. And then is it a solid waste? And if, unfortunately, the word solid waste is a bit of a misnomer here. Actually, solid waste per US law is a solid, a semi-solid, a liquid, or a gas. So you should sort of just ignore the word solid in front of the phrase solid waste. And instead, a solid waste is just something that's being discarded and abandoned or is waste-like, whatever that means. If you have solid waste, which if we throw a solar panel away, yeah, it's probably solid waste, then you have to decide, is it excluded from the governing law, which is the Resource Conservation and Reclamation Act, or RCRA. And it could be excluded from being a solid waste by a particular specific exclusion, such as radioactive waste or sewage. Solar panels are not radioactive, as far as I know, so they're not excluded from being a solid waste. And then the next option is, are they specifically excluded from being hazardous? And in this particular case, there's a list of exclusions, such as oil and gas waste and spent refrigerants. For some reason, those aren't hazardous. Solar panels don't fall into those specific exclusions either. So it's not excluded from RCRA. Then we have to determine if it's hazardous, and that's where the rubber meets the road. So a hazard has to have either be listed on specific lists. There are specific chemicals that exist in the RCRA list as hazardous, or it has to have a hazardous characteristic. And among these choices, heavy metals fall into the toxicity category. And then one other type of designation is universal waste. And universal waste is a hazardous waste that is so common that it's been streamlined in its handling. And these are often household wastes, such as old light bulbs or batteries, are often categorized as universal wastes so that the people who are discarding them don't have to go through quite as rigorous of a disposal procedure. And throughout the United States, this is not too common, but here in California, starting this year, solar panels are now categorized, if they were hazardous, as universal waste, which greatly eases the burden of discarding and recycling a solar panel. So the next part is, if we have a hazard and we've identified that we have heavy metals in our solar panel, does that hazard rise to the level of being hazardous waste? And this is generally, in the United States, the purview of the waste generator, so the person who actually owns the solar panel and not the manufacturer. But we'll go through this exercise anyway. And in the United States, this is done federally by the TCLP test. I'll get to that in a second. And in California is done by a number of additional tests. This TCLP test is a toxicity characteristic leaching procedure where you put a small part of the solar panel into an aqueous solution. And other countries have their own versions of this leaching procedure, but we'll focus on the US for today. In the US, it's a sodium acetate acetic acid solution that's the part of the solar panel that is taken is soaked in this solution for a period of time, and then that leachant is then analyzed for 40 compounds or so. One of those compounds, as an example, is lead, where the limit, according to RCRA, is 5 milligrams per liter, and that equates in practice to 100 milligrams of lead per kilogram of product, or 100 ppm. One of the important things at the outset is, if it's not possible to contain that amount of lead within your product, then you don't need to do this TCLP test to determine whether your solar panel is hazardous or not. And so the first question to ask is, are perovskite solar panels unequivocally not hazardous per RCRA and TCLP regulations? So the baseline here is a silicon solar panel where there might be some lead. There's always a little bit of lead because of the glass sprit used for the silver ribbons. And there might be a lot of lead if there's also lead in the solder. And the answer of whether or not a silicon solar panel is hazardous is determined on whether or not it has that lead in the solder. So if it doesn't, then it's clearly well under 100 ppm, and you don't even need to do the TCLP test, and you can call it not hazardous. In fact, you can probably just throw it in the trash. If it does have lead solder, then it's well above the 100 ppm limit, and it needs to go through this TCLP test to see how much of that lead actually leaches into the solution. So with that as a baseline, a perovskite panel that is of a similar construction, so glass on the front, polymer on the back, it also has, of course, some amount of lead. And in perovskite solar panels, depending on how thick your layer you're depositing with the perovskite, that's somewhere between 0.5 and 1 gram per square meter. And depending on that number, you're pretty close to this 100 ppm. And so probably the TCLP test has to be done. And then it really depends on whether all of that perovskite, the lead in the perovskite, leaches into the solution to determine whether it's hazardous or not. If instead you make a perovskite panel that's glass, simply because it's so much heavier, then you're probably well under the limit, and you don't even need to do the TCLP test. On the flip side, if you make a perovskite panel that's lightweight and flexible, so a polymer front sheet, polymer back sheet, it weighs so little that at 583 ppm, it's well above this threshold limit from a total concentration standpoint. And so it needs to at least do the TCLP test to determine whether or not all of that lead leaches into the solution. For perovskite silicon tandems, the answer is much in the way of a silicon solar panel. In this case, the driver is not the perovskite. The driver is instead the tin lead solder. And if there's lead-free solder, probably the perovskite silicon tandem falls well under the 100 ppm limit. If it's tin lead solder, then certainly the TCLP test needs to be done. And so it's a bit of a complicated, very product-specific analysis in terms of is a perovskite product unequivocally not hazardous? And certainly all of these products could become not hazardous depending on the results of a leaching test. Outside of the United States, where there are no specific regulations to handle the end of life and waste streams of solar panels, other countries are more likely to be like the United States. So Japan, China, India, other very large solar users also have no specific regulations. These are likely to be forthcoming as more solar panels reach their end of life, but at the moment, nothing specifically is a requirement for throwing away a solar panel. The exception to this is the EU, where through a directive, they have considered all PV panels as e-waste. And in this directive, the manufacturers, the producers of the panels, have their responsibility for end-of-life management. And that equates to the manufacturers of the panels have to recover 85% of their panels. That means they need to go out to the solar farms when that solar farm is being dismantled and put all of their solar panels in a truck and take it away. It is their responsibility to recover the solar panels from the site. And then 80% by mass recycled. So 80% of that solar panel actually needs to be recycled. And that sounds like a really large number, but in fact, in practice, it's a pretty easy number to hit. So for silicon solar panels, if you need to hit 80% by mass to recycle, then that includes the glass, it includes the aluminum, and optionally, it includes the copper, and you can hit 85%. For thin film, such as CIGS and cadmium telluride, that's even easier. In fact, you can hit 80% just by recycling the glass, much less any of the thin films themselves. And so 80% is actually quite a low bar in terms of a full waste recovery, especially of the hazardous portions of the solar panel. The final level setting here to have further conversations about how perovskites might meet their end of life is to talk about how solar panels, when they are recycled, how that recycling process is done. So first, for a silicon solar panel, this is the general process. There are other small-scale processes that are performed in pilot stage, but this is the, by and large, main process by which silicon solar panels are recycled, and that is to take the junction box off the back. The junction box comes with the copper wiring, so by taking that off the back, You can easily extract the copper, send that back through into copper recycling streams, and then remove the aluminum frame. And since that's pure aluminum, that can easily go back into aluminum recycling streams. And then with the main part of what you think of as the solar panel, sort of this glass laminate, that glass laminate is then crushed and then sent through a variety of filtration steps in order to arrive at something that's called glass cullet, which is just crushed glass. And nominally, this crushed glass could be sent back to a glass factory and made into a window or another cover glass sheet of a solar panel. But unfortunately, this glass cullet, because of the nature of how the solar panel is recycled, is a low-grade glass cullet, because in this sorting process, it's an imperfect process, and there remains bits of silicon cells, which contain silicon, but also silver and other metals, as well as parts of the polymer encapsulant. And so this low-grade cullet can still be recycled. It goes primarily into two feedstocks, either to a fiberglass insulation, where at a certain loading ratio, 20%, you can add low-grade cullet into a higher-grade cullet to make fiberglass. And that industry can handle about 1 million tons per year of glass cullet, or low-grade glass cullet in particular. Or you can use it as flux in metal refining. And at the end of the day, that flux turns into slag. And slag is often used in concrete and also as fertilizer. And so this slag for concrete, the size of that market is about 7 million tons per year. The other major type of recycling is for thin film panels, for which First Solar has a well-known recycling process. That recycling process used to be paid for upfront with the solar panel. That ended in 2013. But nevertheless, their recycling process is significantly different. So I'll walk through it here. They take their module and they also break it into tiny bits through a couple of steps, through shredding and a hammer mill. And then where it becomes relevant for perovskites is they go through a leaching step, or actually a variety of leaching steps, where they disintegrate the cadmium and tellurium from the glass into solution. And then they go through a separation step where the liquids and solids are separated from each other, the solids being primarily glass, but also a bit of that polymer encapsulant. And so a final step for the solids is a glass filtration or separation step to separate the glass from the remaining polymer. And the final product of that flow is a glass cullet as well. And then the liquids, of course, bear in solution the heavy metals, the cadmium and tellurium, and they go through a series of precipitation and refining steps to end up with solid filter cake, it's called, of cadmium and tellurium separately that can be sent back in with further refinement into new First Solar panels. So with those recycling streams, the final bit of level setting here is, can we handle that amount of recycling? And is that amount of recycling or waste a big problem in the grand scheme of things? And the answer is that in the United States, by mid-century, 2050, the amount of total PV waste per year is going to be about 1 million metric tons, which is a pretty big number. And worldwide, that number is about 5 to 6 million metric tons per year. That is about 6 to 12% of the total e-waste, both in the US and in the world. And it's about 0.1% of the total waste in the United States. So significant, but certainly come 30 years from now, when we're throwing away 1 million tons of solar panels per year, even if we threw them all away, it's not that your landfills are suddenly going to be overflowing with solar panels. It is a minor fraction of the problem that is e-waste in general, and waste of any type. But at 1 million metric tons, it's also important to think about whether the recycling streams that exist today can handle that volume of waste. And as we said before, the biggest and the lowest grade of recycled material that comes out of solar panels is that low-grade glass cullet, because it's contaminated with other materials and therefore has very limited options for how it can be turned into a second useful life in a different product. But that total amount of available waste stream for fiberglass and for slag is 8 million metric tons per year as of this year, and likely to grow with as we grow into the mid-century. And so 1 million metric tons per year can easily be handled. And so even in mid-century, these existing recycling methods can be handled by the aftermarkets that exist today. If we want to do recycling of perovskites, specifically within this general recycling ecosystem, by the time that perovskites grow into a large fraction of the market, and certainly by the time that perovskites will begin reaching their end of life, the recycling industry for solar panels will have been built even further around end of life of silicon solar panels and end of life of cadmium telluride thin film solar panels. And so it's highly likely that any perovskite specific recycling methods will need to conform in large part to those existing methods. Something that's completely out of the box in order to recycle perovskites likely won't be easy to adopt, nearly as easy to adopt as conforming to an existing recycling method. So one of those methods that I show here on the right from a paper by Paul in 2016 is reminiscent of the First Solar type method, where the perovskite is dissolved into solution and then precipitated out electrochemically, and then that lead can then be used either into the lead acid battery waste stream or converted back into lead iodide to turn back into a perovskite solar panel. Before I get to the conclusion slide, I want to thank the California Energy Commission, who is sponsoring some of the work that we're doing on recycling methods for our perovskite solar panels that I won't talk about today. And then I want to thank a few people from Tandem PV, Chris Sieberspacher, David Maloney, and Terry Banks, who have been doing a lot of this work. And then want to just leave up this conclusion slide as we talk through any questions. These are my takeaways from the regulatory landscape and in solar panels. The perovskite, the amount of lead in perovskite, is dependent on the product form to determine whether it's hazardous or not. Which, if it's not hazardous, of course, you can throw it in the trash. If it's hazardous, then it has to be handled in a specific way. Of course, we want to recycle our solar panels because, we're all here because we want a cleaner world. And so filling up a landfill is a least attractive option. And so in the recycling, the perovskite will need to conform to existing recycling methods. And it's likely that the perovskite will be compatible with those existing recycling methods. And that, in the grand scheme of things, solar waste is a pretty tiny component of e-waste, which is a really large problem throughout the world. To remind everybody that of a solar panel, even though it's the absorber, in particular the silicon, that we think of as being the most important part of the solar panel, that's actually the only part of the solar panel, by and large, that doesn't get recycled. It's the glass, the aluminum, and the copper that gets recycled. And then, unfortunately, due to the laws and regulations around defining hazardous materials by weight, lightweight perovskite solar panels are likely to face the largest regulatory hurdles, even though they're using less material overall, which is normally a really good thing. So with that, hopefully everybody has gained some new knowledge about what the landscape looks like for solar panel regulations and laws and recycling methods, so that we can have a further conversation about how we should best as a community figure out how to dispose of and recycle our perovskite solar panels as we flood the market with them and change the world and turn global warming back on its head. Thank you very much.
Thanks a lot, Colin. That was super informative. I know I learned a lot. I think I had some kind of basic knowledge of some of these regulations, but I appreciate how you broke it down. So our first question is really touching on what you have in the bottom right here about this kind of irony between always wanting to make things lightweight versus regulations being related to the total amount of lead in the whole thing. So do you see that as always going to be that way? So the BJ, who asked the question, said he can easily envision eco-advocates pressing to change this criteria to a unit-based measure. Do you have any sense of if that's going to happen down the road?
It's a great question. And, I think that reducing the total burden of a landfill is always a good thing. And sometimes laws are unfortunately not written in a way that always accomplishes that. And I think here in the United States, we're at the beginning of having this conversation about regulating solar panels, regulating their waste and recycling. Even in California, which is usually considered very forward-leaning on some of these things, they only just implemented a
Whoop, did we lose you?
Yeah, it looks like we may have lost Colin. His audio connection is showing as not connected right now.
Okay.
maybe his phone call just dropped, and he'll call back in just a second. Sorry about that, folks.
Hello? While we're waiting, Joe, I'd be kind of curious, since you're on the line, what is your kind of thoughts towards the way these things are regulated? Do you think it's going to change one way versus another?
I guess, I mean, I would view regulations a little bit like a lagging indicator of technologies. I think this is the point Colin was starting to make, which is that, we have goals for the technology and we'd like to minimize our impact on other elements of the environment while we're solving CO2. Oh, Colin's back. So
there you are. Thanks, Colin. We're just killing time.
I would view that as a little bit of a ancillary thing, but Colin, please.
Yeah, I'm not sure where I dropped off, but where I was headed was, I think it's a great question. I think that it is an unfortunate way that the current law defining hazardous materials is written, but the opportunity is certainly ahead of us to guide the policy at the state and national level for how we do want to treat perovskite solar panels or solar panels in general at their end of life, since there are no current regulations in the United States. So I think that that conversation is still happening, and I think it's just at its infancy right now in the United States. So the opportunities are there to talk to your representatives, to really get this in front of them as something that we need to define in the United States.
Great. Yeah, no, I think that's a good message. So to change gears a little bit, I'm interested in this question specifically for you guys as Tandem and the way that you're looking to introduce your technology. So given that the lifetimes of crystalline silicon and perovskites right now are so vastly different, how will recycling of a Tandem module be managed? So I think the gist of this here is, can you recycle the perovskite and keep the silicon so it can be reused? Or, I don't know, is this something you guys have thought about?
Yeah, it's a great question. And, certainly our overarching commercial goal here is to introduce products which do not change the overall lifetime expectations of the product. So we will be introducing products that last 25 years. And if we can't get there, then we won't be introducing products. Unfortunately, because the encapsulant is designed in general in a silicon solar panel to glue everything together, it's very difficult to specifically unglue certain parts of a solar panel, which frankly is why silicon solar cells are not recycled, because they're difficult to unglue from the encapsulant. The same will be true in general for the perovskite component within a silicon solar cell if we're making a Tandem.
Excellent. And that also answered another question here about why silicon wafers are not recycled. So doing some double duty on the answer there. So another question here, I think this is interesting. So technologically, there appears to be no issue with recycling the materials in perovskite cells, but is it actually financially viable? Do you have any sense of how much it adds to the price, and is it really worth it?
Yeah, it's a great question, and a lot of us would like to recycle everything, so that we don't add anything to a landfill, and that's a great goal. But the first, always the first goal is to make sure that if you're going to throw something in a landfill, that it's not hazardous, and then it's not going to, leach a bunch of lead into the groundwater and change the lives of the people that live near the landfill. And to the degree that we can recycle things, it does matter what the ultimate economic value of those materials are. And for lead's a really cheap material, and it doesn't have a whole lot of economic value. That's why lead acid batteries are so cheap. And so I think it's important. The critical take home here, if there is one on this question, is if we're going to extract the lead, because there is so little value in that lead by weight, then that extraction method has to happen as basically a byproduct of the existing recycling methods. So it has to come out basically for free in the course of having recycled the other components of the solar panel that do have aftermarket value, like the glass.
Right. I suppose in some sense, we are where we are with some climate change because we've always gone for the cheaper thing. And here's a good example of that. We know we should recycle because it would be better, but we always have to consider cost. So it's sort of a catch-22 I think we find ourselves in a lot of times.
Yeah, I would say parenthetically though, just building on kind of Colin's point, right? I mean, the goal that he laid out, right, really is in line with I mean, we're talking about it in slightly different ways, particularly now this administration with questions about justice and inclusion and diversity in the context of technological development. So, these externalities, right? We always pay for it one way or the other, right? When we burn gas, we pay for the CO2 one way or the other. It's just a question of how we're doing the accounting to a certain extent, and being, what's the word, transparent about exactly what we're paying for.
Yep. Great. So to get a little bit more away from some of the recycling issues and more towards the science of tandems, so there's a question here about the degradation processes of the perovskite device and if they impact the IR transmittance in a way that degrades the power delivery to the lower bandgap cell partner. Sorry, this is worded in kind of a weird way. So I think the gist is when the perovskite degrades, is that going to affect the performance of the silicon cell, or can you have a kind of dead perovskite layer and still be getting good energy out of your silicon?
Got it. Yes. So two things to keep in mind, maybe three things to keep in mind. First off, we don't really want our perovskite to degrade that much, and certainly, hopefully not in an optical sense. Once a perovskite's degraded optically, then it's very degraded. But if the perovskite were to degrade substantially, then it's important to keep two things in mind. One is that in a tandem, the top cell, the perovskite, is providing approximately 2/3 of the overall power, and the bottom, the silicon, is providing about 1/3 of the overall power. And so if suddenly the top cell shuts off completely, then your baseline is about 1/3 of the original power, which is probably time to go ahead and throw it away. But if you wanted to keep the solar panel on your rooftop, then once the perovskite degrades sufficiently, if you're aware of perovskite degradation mechanisms, then at the end of the day, it turns into something that's not a visible light semiconductor. It can either turn, it can turn yellow if it's turning into lead iodide, or if you really hydrate it, then it can turn clear. And so you can get some of the power back by transmitting additional light into the silicon below. Whether that's economically useful is an entirely different question.
Great. And then I have a question for my own curiosity. In your early slides kind of introducing your approach, you showed a tandem configuration with a backsheet instead of a back glass. I'm curious if you have any concerns about sort of the breathability of backsheets and the inevitable water ingress that you're going to get from that.
Yeah, it's a great question. We're designing our perovskite in a way that hopefully can conform to all existing product embodiments for silicon, of which the most common is flexible backsheet. As we work through product design, of course, there are probably 3 types of backsheet options that we need to do field testing on. And certainly one is just the regular polymer backsheet, of which there is significant water ingress, which necessitates greater protection of the perovskite at the point of perovskite, which we do develop. And then, of course, the other 2 options, if we can't sufficiently protect the perovskite at the thin film level, then you can use a foil backsheet, which has significantly less water ingress, of course, or a glass backsheet. So we'll be doing product design and field tests on all 3 types, and hopefully we'll be compatible with all 3. But walking in with eyes wide open that the water in the polymer only backsheet may be too large of an ingress to handle.
Great.
So
I think
Colin,
I certainly speak for Joe and everyone that we look forward to hopefully getting our hands on a few of those and throwing them outside and see what happens. We'll talk about that later. Go ahead, Joe.
Colin, I guess I was wondering, like along those lines, right? I mean, here you've primarily focused on what we hope is kind of the lifetime. But it's my understanding that one of the other considerations is what happens if say these are installed on somebody's house and you have a house fire, and these kind of considerations in terms of basically the local environment. Is that something that is also a consideration when you guys are thinking about like the different back sheets? I don't know that there's been a lot of work done, but what I have seen, indicates that glass obviously has got some advantages in terms of releasing if you have kind of a house fire kind of situation or something similar for a industrial building.
Yeah, I mean, it's a great question. It's something we're just getting into as well. It's as a pioneer in this space, First Solar had to go through some of these considerations as well, in terms of their entries into the residential space, and ultimately met with some resistance because of these types of issues. So we'll be working with some residential installers, and I think ultimately the deciding factor here is how residents feel about putting it on their rooftop, and so that's going to require essentially lots of surveys with potential residential solar owners, to determine really how much do they care about the potential for fire, and how much do they care about the potential for small amounts of lead leakage. And of course, there is a big component for the scientific community writ large to figure out exactly what the risks are, how much lead would leak out in a fire based on certain fire temperatures and certain product configurations. I think that'll be really useful for having those conversations.
Yeah, because I think it's a really interesting question, because the data that I've seen was for kind of a single junction perovskite, and in the context of the tandem, you can imagine that that bottom cell could also provide some protection. But yeah.
So I don't want to cut off the good discussion, but I do want to be conscious of the time. We are at the hour and made it through, I think, the majority of the questions from the audience. Colin, do you have any kind of closing thoughts before we let folks go?
No, none for me. I mean, I hope that everybody gained some knowledge here. It is a complex set of issues on how we handle end of life in general, and frankly, installation and operation of solar panels in the United States. And I think it's, as we try and commercialize through a variety of form factors, perovskite technology into the marketplace, it's going to require both, the end users, policymakers, and the manufacturers to come together and figure out, how do we want to handle these things? How do we want to come up with a common set of requirements and regulations around the use of perovskites as a new technology in this space?
Great. Well, thanks a lot again for the presentation. I think it was a honest assessment of kind of where we are and where we need to go, and also provides at least me some optimism on what we need to do. So, Joe, any final words?
No, I'll just shamelessly plug Colin and Tandem PV, looking for folks again. I'll do that, but I think it was a very thoughtful presentation. So thanks, Colin. Really appreciate it.
I appreciate you guys having me.